you. Oh. Your name is Miss. Thank you.
I had a good turn this in.
Yeah. Thank you. All right, so today we'll do just a review. So going over some problems, answering questions, of course. Just a couple of notes. I've tried to catch up on grading. So I think I did at least most of the midterm corrections. I think I found I missed somebody's. I got more papers. And then I'm still behind on the labs. So, if you've checked your lab grade and it wasn't graded, don't fret. I still have a big pile that I haven't looked at. So yeah, I'll just be working on your grades, obviously. And I haven't touched your lab finals, so apologize for that. And then just get anything that's missing done ASAP. So I will be in lab today. Oops, if I could spell. So I'll be there in case you want to catch me for any last minute makeups, whatever, quizzes. So hopefully those are done. But oh, and then don't forget your reading questions. So right, they're on Blackboard. Don't forget about them. Do them. They're worth like 5 or 10% of your grade. I have to look at the syllabus again. So don't forget about them. Let's. All right, let's just try an equilibrium problem. Just do a warm-up. So we're looking at this reaction, so A x5 and solution reacts to give us A x3 plus x2. And these are all in solution. And so then we found that our Kc, or we're given, is 0.0677. And then we initially have 1.55 molar solution of our AX5. So determine equilibrium concentrations. So to start with that one, and we'll go over it. Oh, it's like a molecule.
Oh, that's the correction.
Yeah, those are like the points, yeah. I haven't scaled it and added it or anything. All right, let's start kind of walking through this. So what do we need to do? What's our setup?
We need to start with the rice table.
So do our rice table so we can rewrite our reaction if we need to. And so what are our initial conditions that they gave us?
We start with 1.55 moles of OX5 and 0 moles of everything else.
So 0, 0, and then luckily for us, right, with 0 products, we know which way the change is going to go. So what's our change then?
1.55 minus x. Or
Or yeah, that's the equilibrium. So minus x, and then
plus x.
plus x. And then now we can add our values, get our equilibrium. And so now we can set it up, just math at this point. So again, we're given our Kc. We can write our expression. I'll just write it in terms of symbols first. So that equals 0.0677. And then to make sure you do the algebra correctly, I saw some funky algebra on some people's quizzes. And we can talk about the quiz too. So then, right, just algebra from here. Let me pull up my calculator. So then, at least I get something like this in the quadratic form. And then plug it into our quadratic formula. And so what do people get for x? Vaughn, what'd you get?
Rounded, I got 0.292.
0.292. Yeah, that would make sense. And then, is this what?
It's 0.1258 for the reactant.
What?
The
Oh,
moles
the,
afterwards.
sorry, you're talking about the equilibrium. So yes, everybody gets this for x, or you're just ahead of me? And then like you were saying, so you took 1.55 minus this to get our equilibrium value. So that's what you said, correct, Hunter?
Yeah.
Perfect.
That's what I got too.
All right. Let me rewrite that. So that was AX5, or we could write this up top now. So then our answer, so AX5, plugging that in, 1.258 molarity. And then the other ones were both X. So both 0.292. Any questions on this one? So just make sure we're doing the quadratic.
Are we gonna be doing any rate laws that are like, half or some decimal, as to construct any?
We probably won't see like the half integer stuff like we did in lab. Yeah.
Will you go back to your quadratic?
I do.
Other questions?
How does this differ from, equilibrium equations where you're using queso A for queso 1, queso 2?
So I guess it depends what you're asking, right? Because it's still a K, and it's still like,
Yeah, it's queso B for a base and queso A for an acid rate.
yeah, so those are more referring to like specific equilibrium situations, right?
Yeah.
Where this is just like any general equilibrium expression. And
Do they all follow this general pattern?
yeah, so that's why it's like kind of repetitive, right, with the rice stuff. So we won't, like I said, we won't see it this quarter, but we'll do more stuff next quarter. Actually, on that note, we will see this. So let's try this problem. So let's calculate the pH of a, let's do 0.0023 molar solution of HCN, and our Ka is 4.9, at least according to this value here. Again, you may see different values on the internet. So on your exam, right, I'll provide a Ka. All right, so see if you can solve that. So still thinking rice tables. Yes, 10 to the negative 10. Yeah.
It's very kind of like split with acid if it's associated with this.
Yeah, except you probably formally want to react it with water, but because that's like the proper Ka reaction. But yeah, you're essentially splitting it, but you're reacting it with water. And then you need your, so it's going to make cyanide right now.
Okay, so this is good.
Yeah, so it's still going to take your history of. Yeah, because you're saying that it's going to be making acid, right? The water is going to be taking up the hydrogen, and then that leads to your steam. And then for your exam corrections, they're kind of entered funny in your grade book right now. Right now, I just have a column, and it's points back, basically, and I haven't done any multipliers or additions or anything to it. So yeah, I haven't finished processing it. Like I said, I think I'll give back 50% credit, but I'm just kind of waiting to see, and I might play with those numbers, but that's where that is, so grade book wise.
Can I turn this in later?
Yeah.
By itself.
All right, how's our pH problem going? So how should we approach this?
It's more or less the same approach, except you're going to create your own equation to use by putting the acid on the left side and then having its dissociated parts in solution on the right side.
So that sounds good. So write our reaction with water, which is essentially our dissociation. So I'm going to write it as hydronium, right? You could write H plus, and then with our cyanide, there's our counter ion. So something like this. And so then we can set up our initial conditions. So of course we're just given our molarity, so 0.0023, and then just 0, right now, right? We're just kind of assuming, okay, they haven't disassociated. And then our change, so what do we get for our change? So minus x
It's plus x for everything else.
plus x, and then equilibrium. So this looks pretty similar. And except with this tiny number, I'm hoping we could probably make a 5% approximation. So that might help us with the math. Otherwise, right, we're just stuck doing more quadratics. Oops, and I forgot our minus x here. And so now I'm just plugging it into our equilibrium or right Ka expression, which is still an equilibrium expression, right? So we're just re-emphasizing that. Is equal to, and then we had a small Ka, so 4.9 times 10 to the negative 10. And so at this point, right, we could make our 5% assumption, so right, that our x is probably less than 5%, at least assume. Again, I'm just looking at that number is pretty tiny compared to this number, right? -3 versus -10 on order of magnitude. So then that makes our algebra a lot easier. Otherwise, again, you're just forced to distribute and go to a quadratic. Oops.
So because that K constant is so small, it really isn't going to be changing that much?
Yeah, at least right for this value. So comparing, yeah.
Okay.
And so let's sort of just trying to verify that. So this is what I got for x. Is this what other people got?
Yeah.
So about 1.06 times 10 to the negative 6. Again, we just want to verify that it was less than 5% of this 0.0023, right? That's why, again, we could make that assumption. So times 100. So yes, right, it's not even a full percentage or not even 0.1%. So very, very small amount. So yay.
Do you have to square that x for that, for CHEM?
I took the square root when I did it, but then once you're doing the 5, when you do the check, no, you don't square it because you're just checking 5% of this change. Yeah, so then that's 1.06 times 10 to the negative 6 over that amount, right? Because that's where we said it was insignificant to that number. And then it did check out. So, yeah.
The exponent, should we like assume we don't need to use a quadratic?
Definitely like 10 to the negative 4 difference. And then usually 10 to the negative 3 is a safe assumption, but you still want to double check it because that can get on the edge. But
Okay, so then if you were to plug the equation that you would get into the quadratic formula and doing it the other way, would you end up getting the same answer?
pretty much. And if we wanted to be lazy, we could plug it into Wolfram Alpha. It'll be faster. So this is, do you guys ever use Wolfram Alpha? Okay, some people's heard of it.
I think we used it in my differential equations class.
It's just a nice computational thing, although I guess, oh, did it like not interpret? No, I was just talking about how nice you were and then you failed me. I should have just plugged in a chat GPT.
Photomap also does a really good job interpreting.
Come on, Wolfram Alpha. You're letting me down today. What is it doing?
It's thinking.
We're trying to get the first.
I don't know what's going on. Chat, I just wanted a faster calculator. We could have already solved it with a quadratic at this rate. Come on. Solve this equation. Thank you. Keep going. What was our x? Oh, geez. Come on.
Wait, if you click the button, right there you go. Wait, no. So dumb.
What is that?
Oh my gosh, I put what is z. Now I've just shown how much failure ChatGPT and everything. Okay, let's try Wolfram Alpha again. Now they're racing. No, solve for x. We're trying to be lazy. Oh, jeez.
I think that ChatGPT has also been trying to make sure that students don't just copy and paste their homework into it.
There we go. I think we're trying to. Okay, yay. So it gives us two possible solutions. So I'd probably want to like manually do this at this point now because it took so long. But essentially, yeah, you would get something that should be pretty similar, right? So they came up with 3.36 times 10 to the negative 6, and we said it was 1.
I got one.
With the quadratic, or?
I used the quadratic.
So yeah, I might trust your quadratic. Now I don't trust ChatGPT. And Wolfram Alpha let me down. But that's kind of the idea, is you should get the same answer either way, or close enough. And now Wolfram Alpha will never compute now for some reason.
You have a question?
Oh, sorry.
I was just clarifying, so when we use a quadratic equation, we don't ever take the negative answer, right? We look at the positive.
Well, yeah, so then you have to check it though, like with the formula. So, right, when you have a positive x here, that's a lot easier to just be like, okay, yeah, negative x, we can't do it. But if everything is like something minus something, that you might have to test, right, the values. And then, so just as a recap, reminder, so right, looking at your quiz then, the quiz that you just got handed back. So right, if you didn't do question 6 correctly, well, that was another rice table. So we could work it out if we wanted to, but just kind of write the same concept again of rice.
Is the entirety of the term going to be on the final?
No, so it's mainly going to be focused on like, right, our equilibrium expressions. And so let's take a look at another type of problem. And this might go back to your question, Hunter, of what kind of equilibriums and Q's and stuff, or K's, I mean, that we're going to see. And so don't forget, we might have to do this sort of scenario. So we're given an equation. So 4 equivalents of A plus 2 of B gives us this molecule of 2 equivalents of A2B. And we're trying to find, of course, our equilibrium. And then we are given these other subsequent reactions. And so then we have A2B plus B gives us A2B2. And we're given that K is 2.22. And then given this next reaction, so 2A plus 2B gives us A2B2. And then this K is 10.5. So see if you can calculate Kc then.
We're not working with facts and so elementary steps in this one, are we?
No.
Where did you get these numbers? Sorry?
You mean K1 and K2?
Yeah.
They would just be like given to you.
Oh,
Yeah.
okay, thank you.
So how are we doing on this problem?
I've gotten to a point where I know that we have to flip one of the equations so that A2B2 cancels out both sides.
So do you know which one you want to flip?
I went with the second equation. It probably would have been better to do the first one. Because it gives you the, or no, actually,
So flip.
no, the first one.
So flip the first one, okay. And then do we need to do anything else?
At that point, you can cancel out A2B2 on both sides because it's the common reactant on both sides. And then there's also 1B on both sides that you can cancel out. And leaves you with A2B, or 2A plus B against A2B.
So then, what else do we need to do? Yeah,
In the overall equation, we need to double. There is double the amount of products and reactants, so we have to multiply the second equation times 2. And also to find the new K1 value, we just inverse it.
so we inverse K1, and then do I need to multiply this one as well?
Yeah, multiply it by 2.
Now we have 1 over K1 squared. So times 2. And double this one, 2. All right, so now, let's see, we gotta make sure everything cancels. And then this will be K2 squared as well, once we get there. And so then just double checking my canceling. So 4B, so now this goes to 2B. And those still canceled, like we'd mentioned. Okay, so then it looks like we're left with 4A plus 2B gives us our 2A2B, like we were looking for originally. And so now we just have to do the math. So right, we flipped 1, we had to square them. And so then that gives us 10.5 squared over 2.22 squared.
I got 100. No, never mind.
Okay. Or double check. Did we get 22.4? Yes, no. So you want me to just zoom out? Yeah, so we started with this, flip that, then we times it by 2. That times 2.
In the book, they related to find the K constant, they related the two constants to each other and then canceled out the concentration. But I don't know if this is related, that would be related to this. So they did like K1 times K2 and they subbed out the rate constants for those and then canceled out. But then I got lost on that. So.
Yeah, I mean, that's essentially what we're doing, right? Because normally you would multiply them together, but then it's just we had to inverse one, so that's why this ended up on the bottom. And then this is still squared, right, like it should be. So that should follow. So yeah, we should get 22.4 for our new rate constant.
multiply them together to get to the final answer.
Yeah, so right, that's all I did was multiply them together, but it's just one's on bottom, right, because we flipped the equation. Let's try, do a different type of reaction. So let's just start with this problem. But then we'll probably go back and look at a quiz. All right, so just try this. So what's our rate law for this one based off of our mechanism here? So NO squared times H2, so exactly, times K equals our rate. So does that make sense, right? So we're just saying, okay, our first step is our slow step, so of course it's going to be dependent on this. And then, right, it just so happens that there also are reactants, so we can just leave it in that expression.
And do you always go with the slow one? Like that?
Correct, yeah. So then let's look at our quiz again. We'll look at a problem, but then we'll kind of take it another way. So I think this was on your quiz from chapter 18. So first it would ask you, so now we have a two-step mechanism. It tells us our second step is rate determining. So what's our reaction in regards to B? So take a moment and kind of remember that. And we could even write our reaction mechanism. So again, right, it's telling us the second step is slow. And so we can break this down, right? So we're saying that our rate, if we're just following, right, this example, well, it's dependent upon the slow step. So our rate is C times A times whatever. Well, I'll call it K2 just because it's the second one. But then what's the problem with this equation? Unlike this first one here. Yeah.
There's no B. And it's asking us to find the reaction, the rate order of
And not only is B not there, because that's not as bad as the fact that we have C, right? So that's the bigger problem.
It's an intermediate.
Right, so right, C is an intermediate here, so it's not a reactant. So we shouldn't be expressing our rate law, right, in terms of intermediates is what we're trying to say. But then we can rewrite it. And so now we can go into, right, our rate law expression of just, so our K1, so this is just, right, our equilibriums. Now we're saying K1 is equal to our reverse reaction of Kc, right? Remember this expression. And so all this does is allow us to solve for Kc, or for C, excuse me. So C is just equal to, right, nu K of A, B. So then what's our new rate law given our C expression, right? So we have to plug this back into here. So what's our rate law?
It's like a squared,
So A squared B now times whatever K. So excellent. So then what was the answer to the quiz then? So what order is it with B?
First order.
So first with B, but right, something else to think about. And again, this quiz didn't ask for it, but then what is A's order?
Second.
So second order in A. And then don't forget the other question that we could ask. So we could say, right, what is the overall order of this reaction? So do you remember what that is asking for?
It's asking for the highest one.
It's asking you to add them, basically. So,
So that's third order.
yep. So then, yeah, it becomes third order. So just remember that last question. So then you add up whatever exponents, and that's your overall order. All right, that might be a good place to take a little break. So, right, think about what other questions and types of problems you're going to go over. I'll put some problems. So we'll probably look at more rate laws stuff, but again, right, if you have questions, ask. Oh, and I was going to say, so yeah, don't trust ChatGPT. Wolfram Alpha finally calculated. It was having an issue with this expression for some reason. But it came out with the number of 1.06, so I like that. And that would make a lot more sense, right? So we can see where our approximation is really valid, right? Because we're only off by 0.06 times 10 to the negative 6 by our 5% approximation. So yeah, who knows what math ChatGPT was doing, but. All right, so yeah, let's take our little break.
As far as extra credit stuff, which video was it for the lecture? I see this one.
Yeah, that one.
Okay, this
Yeah.
one.
The earlier one was from,
And that one's not.
oh, I can't remember. Did I say I was going to give credit for that one? Yeah, I don't remember about,
Okay. And then
definitely
on
that one.
the grade book, showing your registration for spring, is that?
Oh, I wasn't doing that this
Okay,
year.
okay. So that's-
I did turn in my lab, or not my lab, my journal article, the article from last week. I just want to make sure you got it via email.
Oh, like the paper?
Yeah.
Yeah, I just haven't graded any
Okay,
papers.
I was going to say I can also turn it in paper if it makes it easier for you on Thursday, or would you
Uh,
rather just prefer email at this point?
Yeah, I can probably print it, so it's okay. Yeah.
Okay, don't
Yeah.
worry about it then.
Yeah.
Okay, just want to make sure. Thank you.
So is this period going to be over after long because you're doing hour takes today?
Yeah, well, we're just ending at 1 since that's our normal class
Okay.
time, but yeah, if you wanted to go over to the lab and just work and study or review more, that's fine.
Okay, yeah, I was just wondering because I might need to leave right now, but I just wanted to make sure that I wasn't missing anything, so.
Yeah, and you can catch the rest online if you need to, but.
Thank you.
So, I had to, I know I have lab today, and I had to, the only time my therapist was available for appointment was today at 1:30. So, would you like me to still do this, do the equilibrium lab, or, I'm also fine with just, because I've done good on all the other labs, just not doing it. It's up to you, because I know that it's a time constraint for you.
I mean, I'd rather you do the lab.
Yeah. I can also, I should look at the lab report. I could also start it and then come back to it if it doesn't need constant watching.
No, it just needs yeah,
Yeah.
and it depends like how many times you have to remake your solution.
Yeah, I'm pretty precise usually, so I don't think that will be the biggest of deals. Because what time are you wanting to be here till today?
I mean,
I will just come in directly after my appointment because I'm staying in.
okay.
Yeah,
Yeah, that should hopefully be okay.
yeah.
I'm just
I
gonna.
just wanted to let you know. I apologize for not letting you know sooner.
All right.
I did plastic degree. Yeah. Yeah, it was such a short study too. It was like 8 pages, and it was just on like identifying mushrooms and wood. It was like this really quick short study. Like honestly,
months over the spring break.
When I saw on the BCS, it was like, you just have to put in a footnote to the reference document.
Sorry, is that what you were saying? Yeah.
Yeah, it's just like one.
Oh, no way. I'm driving up to Portland on that. Yeah. There, I'm driving up Saturday with one of my friends' kids, in a punk band. They sometimes be like, go drive up to Portland. Yeah. You know who what also has a really surprising Alice. Yeah. The last because you're transferring this call too, right? Yeah. Right. You care. Here. Why didn't we? Yeah. That's funny. Well, that's great. No, I didn't.
Before the guy named us. Paper technically on
I bought the biology book online, and then they like remove stuff like that. And I was like, fine, I'm just gonna find it online.
Are you also forwarding on MSRP? What the? Why haven't we talked about that? Yeah. Well, I guess we'll be calling. Yeah, no, I've been into thorium because I yeah, yeah.
It's like a senior It's kind of like a senior project.
SQL engineer, he, founded,
Like for the entire year, right?
yeah, he's in, Colorado.
Yeah.
Yeah, I love thorium.
Sorry I'm late. I had to go back and do my dog station. Do you like dogs?
Yeah, but we're about to start right now. All right, so let's continue. So yeah, let's just try this one. It goes through the metabolic process of how alcohol is metabolized and first produces acetaldehyde. And so then here are the rates. So you have initial molarity rates. So see if you can figure out rate law, rate constant.
This is a question that would be on the final.
Potentially, yeah. So what do we notice about this problem? Yeah, Vaughn?
The rate doesn't change.
So rate doesn't change. So so that's good. So we're just looking at our data, right? So our rate. And it doesn't matter what our initial concentration is, it's always 2 times 10 to the negative 2. So then what does that tell us about our rate law?
It has to be 0.
So it has to be 0 order. Excellent. So write 0 order. So then, right, that just means that our rate is equal to our K, right? It's equal to our rate constant. And so obviously then it's equal to this. So 0 order. Excellent.
When you express a 0th order rate law, do you include the reactant at all for each?
No, so I wrote it here, right? So it's just, yeah, your rate is equal to K. I mean, if you wanted to be, you know, explicit, I guess you could put this to the 0, but that might just confuse people.
It also means that if you have any other, like, you know, molecules that don't involve themselves in the rate, you have to include all of them. So,
Yeah, but yeah, so I wouldn't really include it, right? Let's try. Let's try one of our Arrhenius equations. So we have the rate constant for a first order reaction is 5.5 times 10 to the negative 8 at 25 degrees Celsius. So what is the rate constant at 50 degrees Celsius if the activation energy is 1 times 10 to the 5th, excuse me, joules per mole. So what equation do we need?
what chapter is this covering?
It's probably 18, yeah, 17 and 18. So what equation do we need for this? And then what do we need to remember? Yeah, I want to go for it.
Yeah. Natural log of K2 over K1 equals EA over R times inverse of T1 minus inverse of T2.
Excellent, like that, correct? And then what do we need to remember about T?
Kelvin.
So temperature in Kelvin. So I forgot where I was looking. It might have been the labs that I was grading where people forgot to convert temperature to Kelvin or something. I remember looking at that. Don't think it came up on a quiz, but yeah, so just watch for that. Your temperature needs to be in Kelvin. Just glancing at our quizzes. And so the other thing to keep straight is, again, it doesn't matter who's K2 or who's K1, just match the appropriate temperature. Excellent. So then just plug it in. So we have to solve for K2. I'm calling what we were given K1. And activation energy. And then don't forget the R is, of course, the energy one, right? 8.314, since we have joules here. Oops. Plus, minus.
Is R a defined constant?
Yeah, so it's just the gas constant. So like I said, right, it's the 8.314 since we're in joules. So joules, moles, Kelvin. So any energy calculation is that one.
On the exam, will we be given the specific R value using the end problem? Or are we supposed to know?
I'm not sure. I think it depends if there's negative signs or not. I did give you the R, so yeah, that was on provided. All right, so what do we get for K2 then once we solve this? And I can also go through it too. So yeah, we're just punching at this point. So that's the other thing, just watch order of operations on your calculator. I think it was on the latest quiz, when calculating the K value. I could tell people were not doing correct parentheses when punching into the calculator. Yeah, question 2 on our chapter 19 quiz had that issue. All right, so and double check the math, but right now I'm here is equal to 3.12 roughly. Does that sound about right? Okay. And then remember to get rid of the natural log, you take each one to the e power now. So this goes away, leaving us with K2. And then I just need to ask the calculator what this is. And of course, using this E button. And your calculator should be in natural log. Just again, double check that as you work this example problem. And let's now multiply. So I get a final K2 of something like this, 1.25 times 10 to the negative 6, roughly.
What are the units for that?
Remember, K doesn't have, yeah. Other questions? I'll get on that one. Let's try another problem. So see if we can try this one out. So we have A gives us C and D is second order in A. We have our rate constant and initial concentration. So what's our half-life? So at least start walking me through this problem of what we're thinking. So what equations do we need, or?
The second order, and the half-life expression is T, the half equals whatever K as the initial concentration. Plug it in, the values 0.82, 0.82.
Excellent. So yeah, it is right this simple. So I would look at your rate law cheat sheet for this, and this is just straight off of there, right? So pulled the formula, and then just like he said, okay, let's plug in these values, right? We're given our rate, we're given our initial concentration, and then I think you, what was the seconds you said?
0.83.
So 0.83 seconds then. You could probably give it another sig fig, but yeah, something around there for that one. 8.26 will be. Questions on that one? So again, right, have your rate law cheat sheet handy. That'll probably be super useful. Let's try another one. This one's kind of fun. So this is another example of kind of a real-world application for some of these. And so we'll kind of, again, talk about this a little bit more as we get into third quarter. But basically, right, usually you can measure some sort of stretching frequency, or maybe these are colored compounds, just like we did, right, with our spectrophotometry lab. And so then what's cool is you can figure out, right, the energy needed to go between these two oxidation states. And so now we're given two sets of temperature data and rate. So see if you can determine the activation energy. And so again, right, that'd be super relevant for research purposes. So how's this problem going? What equation do we need?
Would it be, K equals AAB, negative VA over RT?
I think you could get there. I just had it, I had mine in the 2-point form already. So the natural log of the K2 over K1 again equals the EA over R. So that's the one I used. That being said, right, there might be other forms where you could still get the same answer. And so, right, we're already given temperature in Kelvin. We're given a rate. I'm going to call this my T1 and K1. So then we just need to solve. So if y'all let's check my math on this one. So, right, R is still 8.314. So then let me know what you get for your answer. So I got this roughly, which would be about 89 kilojoules. So do we get this?
Most of those activation energies are usually in kilojoules, right?
Yeah, because remember your answer will be in joules based off of this constant, but then, yeah, it's better to put it in kilojoules. Yeah, so about 89.5, we'll say, kilojoules per mole there. So other questions? So yeah, I'm just kind of looking back at our old quizzes and
Are we gonna have this running like PV equals nRT problems? That has a different value for the R constant, right?
yeah. Yeah, because that one is 0.0821.
3.0826, right?
Yeah, depending if you want to take the rounded form. Yeah, I don't think we will have gas laws. So I think we've mainly covered most of it. Maybe let's do this easy one. Quick sanity check here. So what's the pH of 1.11 times 10 to the negative 6 molarity of NaOH? You have an answer?
Yeah.
Well, let's just give people a minute. So walk me through this. How do we approach it? Yeah, you want to?
Since NaOH is a strong base, I just took that molarity and put it into the negative logs to get the pOH, and then you do minus, and you do 14 minus the pOH to get the pH.
Excellent. And right, you could have done other ways to get there because you could also plug this in for KW if you prefer that, right? Hydronium times hydroxide equals KW, right? Which was just 1 times 10 to the negative 14. So same thing as this approach. So again, that's kind of the nice thing about the pH chapter. So let's just go this method. I think it's easier. Again, there's really no difference. So log of this. So that gives us our pOH, and then 14 minus that. So I get a pH of 8. Is that what other people got? Excellent. So pH equals, so 8.05.
Can you describe sodium hydroxide as monoprotic, even though it's not an acid?
Oh, well, that, yeah, I wouldn't describe it as monoprotic, right? Because it's a base.
Is there a word for it?
I mean, I guess you could say like monobasic, or it only creates one equivalent. Because actually, we could talk about that. It won't come up on your exam, but that does bring up a good point. Of let's say we had 1.11 times 10 to the negative 6 molarity of calcium hydroxide, right? So that does make 2 equivalents. So you would have to account for that in the pH, right? So then just formally writing out our dissociation. So then we make 2 equivalents of hydroxide, right? So now we effectively have 2.22 times 10 to the negative 6 molarity for our hydroxide concentration in that case. So yeah, do watch out for that. It won't actually come up on your exam. I was boring and picked sodium hydroxide, but that. This one just.
No, the earlier.
Oh, the. I could find it. Yeah, this one.
And what was the question asked?
So it just asks the pH.
And then, so how come you didn't go through the rice table? I know that there's this other method, but you still go through the rice table with your answer, or is it asking different things?
So what, it's asking the same thing, but what's the distinction?
Sodium hydroxide is a strong base, so it doesn't really have an equilibrium constant. It's just assumed that it takes up the entire.
And the other one is an
Yeah, well, the other one has equilibrium, right? Because we could still do, find the pH of a basic salt, right? We would have similar equilibrium. Does that make sense?
but I think that's
Well, it goes back to being, right, a strong versus like a weak acid, or, so it's just who disassociates. So that's all right. He was saying when you have the sodium hydroxide, right, it's strong, in the sense that we know that all of this is then converted to hydroxide, right? All of it is going to disassociate versus the first one that we did, we have some sort of Ka expression, right? And we could do another practice, if people want another rice table practice. I'll change it up a slight bit. So now let's look at let's calculate our pH. So calculate our pH of a 0.88 molar solution of sodium chloride, given that our Kb of fluoride is 1.48 times 10 to the negative 11. So just think about your rice table first. Think about how those problems are different, right? We can't just plug in our 0.88 into our concentration, right? That's the whole point. So now we have our Kb.
That's saying AB times alcohol? Like with the little,
I'm saying the Kb of the fluoride, because you have to now write the equilibrium constant. And then, I'll kind of help y'all along a little bit, but since we haven't done Kb too much, but you still want to understand what your reaction is saying. So we're saying, okay, I'm going to take my fluoride, react it with water, because again, water is going to disappear anyways. And then we reform our acid. And then, so there's our base conjugate acid relationship. So just thinking about questions like that. And then, of course, definition of a base, though, is that we form hydroxide. And so again, that's the difference, is now we have to solve for how much disassociated versus taking it for granted that all of it disassociated. So then the rest should just kind of follow at this point. So minus x plus x plus x, just like before, right? Just now we're looking at Kb and solving for hydroxide. Equilibrium, looking pretty similar. And then I'm probably going to take, some liberty there. Assume our 5% approximation is valid. So first I'll write it. So equals our Kb. So assume less than 5%. So now we're just left with x squared over 0.88 equals our KB. And so now we can solve.
So we really want to pay attention to those, whether it's a weak acid or the dissociation.
Yeah, exactly. So we'll hang on to your thought for a second. I'm just trying to finish. So x equals blah, so 3.6 times 10 to the negative 6, which we said, right, was our hydroxide concentration. So now we can plug it in and at least get, right, the POH and then the pH. And then, yeah, to follow up on your point, all this is to keep in mind, right, who's our strong acids, who's our strong bases. So I would just go back to that chart, which I think I printed out. And I probably have more hiding in my office if you need more. Where's that chart now? So, right, this one right here, where it's talking about who fully disassociates, right? There's our fluoride, so we can remember, okay, it is weak, right? It has some sort of equilibrium. So that will also help you is identifying, right, these ions here, and maybe you could make little cheat sheets, right? Because then you can start saying, well, these are my conjugate bases of these acids. So these are also going to be basic salts. So hint, hint, right? So any like sodium fluoride salt is basic, sodium nitrite is basic.
I like sodium chloride.
So then what's sodium chloride though?
It's sodium chlorine.
Yeah, and then would it be acidic, basic, neutral?
I don't think it would be neutral. But
Yeah, exactly, right? So then hydrogen chloride though is part of the strong acid, so it fully disassociates, so it's neutral, correct? Yeah, so keep that in mind, right? Like all these, so bromine is neutral, iodide are neutral salts, right? We mentioned chloride, there it is again. Nitrite, these are all neutral. So maybe we should add that, right? They tend to be neutral. Obviously, you have to check the counter ion. But then, right, all these are going to be basic. Obviously, hydroxide's basic, but, right, we're seeing that.
So then everything in between is partially dissociated.
Exactly. So all these in between, then once you recognize, okay, it's something in between, so it's equilibrium constant, and then, yeah, Rice table and all that good stuff.
So then can you go scroll up on that page? Past that next to the original one.
Oh, sorry. So yeah, that's basically the review I had prepared. I can give you a quick rundown of your exam. Let's see, it is 16 questions that are multiple choice, and then those are all worth 5 points. You have some easy free response, we'll call it, that are worth 5 points. What I call slightly higher free response were 7. Again, what we've done though, right, finding activation energy or something like that. There'll be one where we have to find the equilibrium constants by manipulating the equations, right, like this one. So expect to see one like that. Expect to see pHs of both weak acids and potentially, right, strong bases. writing our rate laws, so writing rate law expressions and reactions. So yeah, hopefully it won't be too difficult. I think I dialed it back a hair. All right, any other last minute burning questions? So like I said, I'll probably be hanging out in the lab, HEC 312. I think I'm running one last makeup final. And so yeah, if you have any missing quizzes or just want to sit in there and work, I will be there. All right, I will see you Thursday. Good luck studying. If you're on stream, ask your questions before I end it. Oh, there's like a rough study guide on Blackboard, but it just kind of lists the topics.
Okay.
Yeah.
One of the questions that we went through for this one, how did you solve with the EA again? Because I solved with this part, and I can solve with this part, and then what do you do next?
Oh, so you just have to keep going with the math, right? Because that's a number, that's a number. So then you should be able to move this over, so divide by whatever this equals. And then multiply by 8.314.
Okay.
And then that should give you.
Alright. And are you still doing like spring registration?
I probably wasn't. No.
Wasn't? No.
No, that's just not Blackboard legacy.
Okay.
Yeah,
And are
because
you
I'm
gonna,
giving extra credit out for other things.
Yeah. Are you just gonna do that for like? Have you get like the sign-in sheet for the second guest speaker that we have? Because I went to the guest speaker, but I don't know if you got the sign-in sheet. I'm sure I just email you.
Yeah, email me because I didn't get a sign-in sheet, but I could ask Tony about it too. But
Okay.
yeah, it'd probably be better if you just email me.
All right.